Questions to hear? All right, 2 more vocab words. Insulator and conductor. What's the difference?
One promotes current and one kind of stops it.
The spirit there. I wouldn't say conductor promotes it, it allows it. Would be
Yeah.
my thinking, but. So in an ideal insulator, nothing is flowing. Now there is no ideal insulator, we can get better and better. In other words, greater and greater resistance, but ideally, no charge movement is possible. Now, for those of you not used to my handwriting, I will say that when I did teach elementary school, I made sure I wrote very neatly. When I stopped teaching elementary school, I thought, I don't have to do that anymore. But then I kept having students say, what is that? I can't read your handwriting. So please feel free to ask if you can't read my handwriting and not quite sure what I just said. So in a conductor, electrons, so it's a medium through which electrons flow easily. I can put easily in quotation marks because that's a nebulous term. Later on, we will tack on the term resistance in order to describe how easily electrons can flow. All right, let's do a little bit of a demo. Let's set it up so that people can see. Set it so that everyone can see there. Can everyone see the 2 aluminum strips? All right, so I'm taking a material here, and I'm not 100% sure what the material is itself, but I'm taking a rod and I'm going to rub it against the rabbit fur. Now what's happening is I'm doing this, the electrons are being transferred. And again, this goes back to the rule of most of the time it's the electrons flowing, not the protons. The only way protons are flowing is that when I pull this off, sometimes there's little bits of rabbit fur still on it. Now for those of you concerned about the rabbits, these rabbits, after having their skin taken, man, that was brutal. After having the fur removed, are now living in the warm climes of somewhere near the equator. The rabbits are fine, they're on a farm. They generously donated their fur for us. I feel like when I told it that time, there was a menacing undertone to it. That was not intended. It was supposed to be light and airy. So we have these 2 leaves like that. I'm going to bring this close to it. And nothing's happening. So let's try that again. Any of you who've done face-to-face physics classes recognize that half the demonstrations never work. Ah, it moved a little. Are they stuck? There we go. Notice I did not touch this to the top of it. In terms of mechanics here, we have a metal ball that is a conductor. Metal tends to be a conductor. The casing here is metal also, but there is a small little insulating piece that is keeping this metal ball and rod from touching the casing. We should not be dealing with, at least at this point, dealing with any amount of charge that would spark. So I brought it close to here and I took it away. So for the most part, no charges actually were transferred between the rod and the ball. Now for the sake of this demonstration, let's assume that electrons are being transferred from the rabbit fur onto this. As I bring it closer, notice the leaves separate. And I take it away, and the leaves go back to where they were. Question is why? And I offer it to you. Why did that happen? Why did the leaves split apart, and then why did they come back together again?
Are the electrons between the leaves? The electrons between the leaves, separating them?
Why were there electrons between the leaves?
Because the electrons float.
They do float. Why did the electrons? What are there electrons there now?
Yeah,
So what's different?
there's more of them.
There's more of them now or then?
When then?
Then why were there more electrons then? Why were there more then?
When you move the rod close to the ball, it pushes the electrons out of the ball and the leaves.
So, two of those rules. One, it's the electrons that moved. And two, like repels. If this were positively charged instead of negatively charged, what would we have seen differently?
The leaves would have moved closer together because the top of the ball would have been negatively charged to balance out with the rod.
So if the ball is negatively charged to balance out with a rod, what does that mean for the leaves?
I guess it'd be the same thing again, wouldn't it? Because they're more positive, so they're still pushing against each other.
Yeah. So we would see the exact same thing. This is not a test to see whether this is positively or negatively charged. It's a test just to see if it's charged. It's only a matter of if it's negatively charged, the electrons flow away. If it's positively charged, electrons get sucked up towards it, get drawn towards it, that's a better wording, leaving them positively charged leaves, which will then repel each other. Now, we can have somewhat of a test. This is a little bit trickier. Probably not enough for that one. I got it. All right. So now this time I'm going to take the same rod again, same as I had before. There was no sleight of hand in this. There's something later on where I attempt a sleight of hand and it's horrible, so never trust that I can do sleight of hand. And we're actually going to touch the rod to the ball. What would you expect to happen?
The leaves return to the starting position.
As soon as I touch it, they're already in the starting, so you're saying they're going to spread apart and then come back together again when I touch?
I think so.
Why?
Because you're grounded.
Because
Because you're grounded.
I'm grounded.
Yeah, and you're touching the rod, which is touching the middle.
Ah. Is this rod an insulator or a conductor?
It's an insulator.
I hope it's an insulator. If this were a conductor, what would happen to the electrons that get wiped onto it? Where? Yes. Suddenly I would get charged. So this is an insulator, so the electrons are not flowing along the rod, not appreciably. Let's start with PVC, actually. I think PVC works really well. And the other advantage of PVC is I'm much more confident that it's electrons being transferred through the PVC than whatever that is. All right, so your initial speculation was that they would go apart and then when I touch it, they would come back together. Grounding is not really an issue. Grounding works if you can have the charges actually flow somewhere. But this is an insulator. Charges can flow, on the spot where I touch it, but because this is an insulator, it's not like they're going to spread out. Or go in the other way too. You still sticking with they're going to come apart and then go back together again?
They'll go apart and then they'll come back a little bit, but not all the way, because there's still an additional amount of charge in the system. It gets not at the initial amount of overall charge.
Does anyone want to stand up and go, Colin, what happened to you? Or are you going, Colin, yeah, I agree with you. Sorry?
I think they'll stay apart.
Why?
Because before, when you did not not move the rod away, they stayed apart. It was, you were moving it away from it. So if you keep it there, then the charges aren't leaving, they're still somewhere. I don't know.
Okay, and so when I pull it, so you're going with the scenario, if I come down and I touch it and I stop there, I guess that's the scenario I presented. So as soon as I touch it, you think they're gonna spread apart farther or just stay apart?
They're gonna spread apart quickly and stay apart.
Okay, and then when I pull this away, what do you think's gonna happen?
They're gonna stay apart.
All right, and Colin, what do you
No,
think?
they're not gonna stay apart. They're not gonna stay apart.
They're gonna come all the way back?
Not
Where
all
was-
the way back, so that's the insulator, but no insulator is perfect, so some
Well,
of it may go into the thing.
you're warning you to talk like a physicist already, that fudge factor you throw in there. Colin, what do you think's gonna happen?
I think that after you remove it, they'll slowly return to rest as they just kind of disperse their charge in the air.
All right, I will say, if I've done this demonstration in May, and they definitely go back together again. When it's really humid, this is horrible. All right, so let's find out what happens. Anyone else want to speculate? Show off how awesome you are? All right, so I rig it closer, and they are twitching a little bit, and then I touch it, they spread farther apart. You take it away, they're not completely back together again. Now we can keep them farther apart for a little bit longer. And now they're apart, and I've taken it away. Why is it that when I first removed it, I touched it and they jumped apart, and then I took that away and they came back, not all the way back to rest, but that was badly worded, not all the way back to the original position, still slightly separated, but not separated as much as they were a moment prior.
There's still electrons present,
What did the touching do?
transferred.
There's not enough electrons on that for it to jump the gap, really. Basically, what would happen? What is it called when the electrons jump the gap through air?
Spark.
Yes. So it's not enough for there to be a spark. So as electrons get closer, it's pushing million electrons away. There might have been a tiny little spark at some point, but not significant. Then I'm touching it, it's being repelled, it transferred some electrons. So now there's excess electrons on that. So now when I pull it away, there's still some excess electrons. And so they stay spread apart. When I rubbed it, I was able to transfer more. Because this is an insulator, I touch it, basically the electrons in that local area might transfer. But by rubbing it, I'm now allowing transfer of electrons from all over this. Now how do I get them to go back?
Touch a proton.
Touch it with your finger.
What does that do?
Grounds it.
There we go. Oop, apparently I still have some charge there. All right, so feeling confident that this is negatively charged, that this will be negatively charged, because rubbing it, I'm transferring electrons from the fur onto the rod, or the PVC pipe. I'm gonna transfer it. They're staying apart legitimately long. Now, I'm gonna rub this against the rabbit fur. If this is negatively charged, what's gonna happen when I bring it closer to the ball?
They're gonna spread farther apart.
And if it's positively charged,
It depends
on?
how positively charged it is. If it equals the negative amount, then it'll come back together, and if the positive is more, then it's gonna end up coming back out.
All right, I don't think it's that much positive charge there, if this is positively charged. But yeah, I'll agree with what you said. Let's find out. Oop, looks like this one's negatively charged also. So let's see if we can change that. I'm going off of memory here, so who knows how good that is. So first thing I need to do is neutralize it. Now, if I had a water fountain in here or a sink, I'd just rinse water over it and then hopefully wipe it clean with a neutral object. Still fire? Yep. Oops, still negatively charged. And it is possible that this is just the wrong thing that we use. Glass rod. Straight glass and rabbit fur. Oops, still negatively charged. Glass and silk. Anyone know your materials? Could just be a synthetic. Well, I don't feel like this thing got charged at all. Now, this whole idea of which way it went, did we transfer electrons one way or the other? That's not doing anything. Where's the wool? This way. There we go. That's positively charged. The leaves did come closer together as this was brought near it. Not a whole lot. This is known as the triboelectric effect of the transfer, or propensity to transfer. And there are tables. If you type in triboelectric, you'll get various tables. Let's see, over here. There it is. And I'm not expecting you to pick up the details, but at least see that there's a list here of materials, and if you rub them together, take two materials from this and rub them together, the ones at the top are more likely to lose electrons, the ones at the bottom are more likely to gain electrons as they rub. There is a group at NC State who studies, who basically do tribology, which is looking at the effects of friction, which is, I think, tribo coming from the Greek word for rubbing. So there is a group that's trying to figure out, is there a better formula than the formula for friction that we've all known and loved? All right, questions to hear before we pull out the big gun? Van de Graaff generator. Anyone in here with a pacemaker? I know pacemakers are an issue with this, or some medical condition that you think, I guess you're the closest.
I'm okay.
Okay. And I apologize for potentially asking you to reveal personal information, but this is potentially dangerous if you do have a pacemaker. No! We will not be using this. There's supposed to be a belt in there that I just noticed is missing. But it's moving. All right, so that will come later. I'm looking for the belts. We had a slew of them.
is for,
Not only am I looking for a belt, but I'm making an incredibly exciting recording here. All right, I have to find some other place. All right, let's take 5, and I can take one more shot in my office to see if they're in there, and see if we can get this thing fixed in time to demonstrate it. So, take 5. And when we get back, someone remind me to start the recording again. So hopefully we've demonstrated some evidence at least that charges will repel or attract, and since they repel or attract, there's a force involved. So I give you the first formula of the course, first physics formula even. So if I have 2 charges, Q1 and Q2, the force on charge 2 from charge 1, so the force on 2 from 1, is dependent upon 3 major quantities and then some sort of, and then a unit factor. So it depends upon the charges themselves, Q1, Q2. And inversely proportional to the distance squared. And then I've left a little gap up front, similar to the formula for universal gravitation. There is a factor that really is dependent upon what units you're using. If you get far enough advanced in physics, you eventually get to the point where that you'll be dealing not in coulombs, but stat coulombs. And the coefficient up front is 1, which is a convenient reason for them to do it. But we are not using stat coulombs, we're using coulombs, which is part of the metric system.